Module 4 collectively deals with the field of thermodynamics. Thermodynamics is the branch of physical science that deals with relations between heat and other forms of energy, such as mechanical, electrical, or chemical energy, and by extension, of relationships between all forms of energy. So in a real sense, we return to energy considerations from earlier in the course. Chapter 13 opens with relationships between various temperature scales. Fahrenheit is the temperature scale we tend to use most often in everyday life, but Celsius and Kelvin are scales more properly used in the sciences. Some equations in this course not only work best in one of those two scales, but can only be used correctly if the correct temperature scale is used. This can be a big stumbling block in problem solving. Since Chapter 1, it has been strongly suggested that one should include the units of numbers placed in the variables of an equation along with those numbers, manipulating those units as appropriate to make sure that the unit one arrives at matches the expectation of the variable being solved can help to prevent that stumbling. Measuring temperature often relies on the response of different materials to temperature changes. But not only does thermal expansion help in this measurement, we will also see its application to a broad range of phenomena, especially in fields related to engineering and architecture, where constructed objects need to account for any expansions or contractions that might be experienced due to temperature changes throughout the year. Also introduced is a molecular model for gases and several laws that relate different measurable properties of a gas, such as volume, pressure, temperature, and particle count. These different laws were developed experimentally, usually by keeping one or more variables constant, then viewing the relationship between the remaining two. Thus, Charles' law is used to understand the relationship between volume and temperature under constant pressure circumstances. Boyle's law is used to understand the relationship between pressure and volume under constant temperature circumstances. Gay-Lussac's law is used to understand the relationship between pressure and temperature under constant volume circumstances, and Avogadro's law is used under constant pressure and temperature to give a relationship between volume and the number of molecules making up the gas in a container. Collectively, the results of experiment from these three eventually led to the formation of the ideal gas law, written as either PV equals NKT, where K is Boltzmann's constant and N is the number of molecules in the enclosed gas, or PV equals nRT, where R is the universal gas constant, and small n is the number of moles of enclosed gas. The number of moles is simply the ratio of the number of molecules to Avogadro's number. The ideal gas law is an application of conservation of energy to gases as illustrated in the units of the constants used in either form of the equation. In all instances, as needed, the preference would be that temperature be in the absolute or Kelvin units. Problem-solving tips in our book provide guidance for use of the ideal gas law and the units one should consider using. The rest of Chapter 13 deals with the kinetic theory of gases and the movement of gases or diffusion. This will further amplify the application of energy processes to understand the reaction of gases to certain circumstances. Chapter 14 continues this emphasis on energy and energy conservation with the introduction of terms internal energy and heat. Internal energy is a measure of the total energy of all particles, atoms, or molecules that make up a substance. This may include individual translational or rotational kinetic energy of the particles themselves, vibrational energies, both kinetic and potential energies due to interactions between particles within the substance, and chemical and nuclear energies due to binding of atoms into molecules, electrons to nuclei of atoms, and the binding of protons and neutrons to form nuclei. It does not look at the whole system, a thrown baseball or a dropped vase, and the corresponding kinetic or potential energy such whole objects possess on the macroscopic everyday world scale, nor the potential energy considerations of the individual particles making up the substances interacting with something external to the collection of particles, otherwise referred to as the system of particles. So the gravitational pull of a lead ball on each of the molecules in a beaker of water is not considered part of the internal energy of the water molecules, nor the individual lead atoms making up that ball. Heat is all about the transfer of energy between parts. So it isn't energy in and of itself, but a means of energy transfer. Energy transfer in the mechanical world was explored in problems in which an object's potential energy was changed by lifting it from one point to another by some process, or changing its speed and thus its kinetic energy by some process. One can think of that process as an energy transfer process. Heat serves the same energy transfer purpose when it comes to thermal systems. Three different energy transfer processes, radiation, convection, and conduction, are covered in this chapter. The concepts of heat capacity and latent heats are introduced, again with the more global concept of conservation of energy. Collectively, Chapter 13 and 14 introduce the concepts that address the course competency, use the concepts of specific heat and latent heat to solve calorimetry problems. The final competency, use the laws of thermodynamics to solve basic thermodynamic problems and problems involving heat engines, is addressed in Chapter 15, the last chapter of this final module of the course. The first law of thermodynamics is a restatement of the law of conservation of energy as it is applied to thermodynamic systems. Work, as it was originally introduced and defined back in Chapter 6, and heat, introduced in the previous chapter, are means by which the internal energy of a system can be changed. So either energy is transferred in or out by heat, moving that energy into or out of the system, or work is done on or by the system, or some combination of the two, changing the internal energy of that system. In all cases, we find energy is conserved, and that energy is tracked much as was done when energy was first introduced. The second law of thermodynamics is a statistical law that involves a concept known as entropy. Entropy is a measure of the disorder of a system. Like the change in internal energy that is covered by the first law of thermodynamics, it is the change in entropy of a system that is important, not the individual values of entropy at one state or another. One form of the second law of thermodynamics states that the entropy of the universe never decreases. In other words, in a small region of the universe one might see a bit less disorder, but if one then looks at the entropy of the whole, you will still find some disorder than order, even on the largest scales. Entropy is not conserved quantity like energy. The third law of thermodynamics states that the entropy of all substances is the same at absolute zero on the Kelvin scale. One interpretation is that molecular movement stops at 0 Kelvin. By extension, there is no negative temperatures below absolute zero. It is the absolute lowest temperature. Collectively, the three laws of thermodynamics can have a broad application.